Hello, and welcome back to Cathode Tube. Initially, I was planning on doing a tube profile on this 3BP1A, which is actually the first tube that I ever got, first CRT. But there's a little bit more research I want to do on this, and a little bit more documentation I need to find. So for now, we're going to do a different tube. It's a little bit more interesting, in my opinion, and it's actually relatively new to me. It is a 2AP5 from, a million years ago. The data sheet that I have here is from 1944, so that puts it squarely at about a million years ago. I think one of the pleasures of these tubes is opening them from, taking them out of the box and just seeing, gaining any insight into the world as it used to be a million years ago is really fascinating, especially in such, small ways. The packing paper is, really fancy. It's, normal paper on the outside, but then it's, foam with these, little divots. I like that. I appreciate that. I can only assume it's original because it's an old tube, but I think that's neat. Unwrapping it a bit more, here's our actual tube. It's comparatively tiny, which makes sense because it's a 2-inch screen. Just for comparison, little, petite. So looking over the tube, it's small. It's got the name printed on there in that little hexagon 2AP5. I don't know if any of this is going to be legible, so I'm just going to show you and hope. We also see the really common JAN, which I mistakenly thought meant it was manufactured in January. It's not that. It stands for Joint Army-Navy, which makes sense because if you consider the time period that a lot of these tubes were developed in, basically the way I think about it is, if it was made during the Cold War, it was made for the Cold War. And I guess, now that I say that, this is from 1944, so if it was made during World War II, it was made for World War II, which makes sense because the whole country was mobilized. And that includes the R&D scientific aspect of science? Well, I don't know. So this was a tube that was used in military applications. Also visible on the tube base is the logo for the brand, which is National Union. I love these old brand logos. I love them. The little lightning bolts are so cute. It is 11 pins. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 pins. And that's also in the data sheet. It says it's a small shell Magnal 11-pin base. The name of the tube tells us a lot of information about the tube. 2AP5, starting with the 2, it indicates the usable screen diameter, which is 2 inches. That one's really easy. The A indicates that this series of tubes was one of the first registered with the Radio Manufacturers Association, so it's the RMA number. At least as far as I can tell, that's what that means. So if we look at like a 3BP1A, that tube is from a later series, and when we get to that tube, we'll talk a lot more about the development of it and what the A indicates and all other stuff. But the P5 is the most fun part of this tube, which indicates that it has a blue phosphor with a short persistence. I like that. I like these blue tubes because a lot of tubes are like this oscilloscope here, and they have a green phosphor, which is really pretty and it's really easy on the eyes. But it's very ghostly and it's fun. But there's something about these blue phosphorates that is just really beautiful. They're like little laser sapphire. Yeah, no, that's it. They're like little laser sapphires. I think there are sapphire lasers, so maybe I shouldn't say that. So now that we know where this tube came from and what, I don't know what its name means, I don't know. We'll take a look at the data sheet and talk about some of the important numbers we see on there and talk about some of the less important numbers. Yep. So I've pulled the data sheet out of my little binder of notes and documentation and stuff like that, so you can take a look at it. Right at the top, it says Tung Sol, and it says 2AP1. The information should be like close enough. The 2A series is the most important part of it. P1 is a green phosphor, which you can see here. It's a number 1 phosphor with a green fluorescent screen with medium persistence. It's an electrostatic tube, so it uses electrostatic deflection and focusing, with a heater voltage of 6.3 volts of AC or DC. Funny enough, despite the fact that you can power this with a 6-volt DC signal, you don't really want to do that typically because the cathode has to be tied to the filament. So that if you have like a 6-volt DC potential and then you have like a negative 100 volts DC potential from the cathode, it's not gonna work. So you don't want to do that. You typically will want to use an AC supply for filament voltages. Okay. So there we see it's a glass bulb, no shit. We have a small shell Magnal 11-pin base. Finding bases for these CRTs is actually one of the most difficult parts of it. And I don't bother usually, but soldering wires to the pins themselves is really bad practice, so I think I'm going to have to start, doing the labor to find the parts. The way these datasheets are usually structured is that there's like a maximum voltage rating section and a typical conditions section, and then there's some more caveats and stuff on the back. So the maximum rated voltage for the second anode here is 1100 volts. That tells us a ton of stuff about this tube right off the bat. It tells us that, for one thing, it is a low voltage tube, in that the maximum potential between the second anode and the cathode is less than 2000 volts. In this case, 1100 volts. That makes sense because it's a small tube, and even though it has a blue phosphor, which typically has a higher voltage potential, it isn't up there with like the P7 or the P11 stuff where it takes multiple kilovolts of potential. So one of the other things that we can see here is that the grid voltage should never be positive. And that's because the grid is usually held at a negative potential of the cathode in order to help to create that accelerating potential voltage. The maximum DC heater cathode potential is 125 volts, which goes back to what I was saying earlier, where the maximum difference in DC between the cathode and the heater is 125 volts, meaning that the cathode will be physically shorted to the heater. Sometimes there will be a resistor tying them together instead, depending on the specific voltages and the needs of the circuit. But in general, in testing these sorts of things, I found that you can just tie them together and it's fine. One of the other things that's super niche and very important when you get into high frequency applications, but it's less important for the talk that we're doing, where it's mostly audio signals, is the capacitances between the electrodes, because this capacitance is going to affect the frequency response. Despite the fact that electrostatic tubes are very linear, there is still a frequency response aspect to it. So for designers who were making these super high precision oscilloscopes, like the Tektronix designers, it was really important to know exactly what the capacitance is so you could plan and correct for the frequency impedance differences. The last section on this page is the typical operating conditions and characteristics. The way this is set up is for two different anode voltages, one for 500 and one for 1000 volts. With this tube, at a P7 phosphor, I don't think that I would be able to get it working with 500 volts. If I could, that would be wonderful, but I doubt it. So we're going to talk in terms of the 1000 volts mostly. So this is just talking through the parameters and what you can expect for operating this tube in a typical application. Where we have 1000 volts on the second anode, we can use 250 volts to get a usable focus and negative 60 volts to get a usable brightness. In these conditions, the deflection plates will operate at 0.1 millimeters per volt and 0.13 millimeters per volt at the X and Y deflection plates, respectively. There's just a couple little things on this page that I want to mention. The first of which is that when you're testing these tubes, and you're not using a jig like I am with like a little driver board, when you're firing up the power supply, it's important that you connect all of the deflection plates to the anode through a 1 mega ohm resistor, because that is going to center the spot on the tube. I'll demonstrate this frequently when I'm building the support electronics for these tubes, but for now, since I'm just demoing them, I'll just be using a little testing device that I have here. And lastly, we have the actual pinout of the tube and the mechanical information. So pin 1 is our heater, pin 2 is our cathode, pin 3 is our first X deflection plate, and you can see that it is closer to the face of the tube. 4 is our first anode here in the middle. 5 has no connection. It almost looks like it's connected to this deflection plate here, but it's not. That's connected to Y1. Here we have A2, which is our second anode, tied down there. Our second X deflection plate, second Y deflection plate, our grid, and then we're back at the heater again. So nothing bonkers, only one no connection, which is nice. I have some tubes that have like 2 or 3 pins that aren't used for anything, which is kind of weird. But now that we understand this tube a little bit more, let's do some testing and have some fun and make some shapes and colors and whatever. in summary, the 2AP5 is a low voltage electrostatic CRT tube with a 2-inch screen diameter and a blue short persistence phosphor. It was used in civilian and military equipment as an oscillographic display, but also the blue phosphors were also used for data transfer and transferring video information onto film. And so the brighter blue phosphor was really designed for that. But anyway, thank you for watching, and if you have any questions, don't be shy. Say hi in the comments, and I hopefully will see you next time. We'll talk about that 3BP1A eventually. Okay, bye.